Hey everybody, welcome to this video. Today we're going to be looking at Hooke's law and elasticity. So basically, simple harmonic motion when it's happening in springs. So let's just quickly recap what we already know about simple harmonic motion. We know that it's any kind of motion where there's a restoring force bringing the object back to an equilibrium position. So if we look at simple harmonic motion, we have a few general formulae that we can use, and then it breaks down into either being a pendulum, which is swinging through an angle of 10 degrees or less in total, or else it's going to be a spring, which is going from extended to compressed past this equilibrium position on its way. We've already looked at pendulums, so today we're really looking at springs. Okay, so let's just look at the idea of elasticity first of all. So any material that's elastic is basically just a material that's able to return to its original shape after it's been stretched or deformed. So the obvious example of something that's elastic is an elastic band. We could also think of things like wooden rulers, which also return to their original shape if you bend them slightly, or really anything that you can bend even a little bit that goes back to its original shape. Okay, so here we come to the most important part of this topic really, which is Hooke's law. So remembering we're talking about springs here specifically for Hooke's law. What Hooke's law says is that for a restoring force on a spring, it's going to be proportional to the extension of the spring. That's the first part anyway. We're going to loop back to the second part. So what that looks like for us, if we were to draw a spring, here's our spring where it's got no displacement on it. If we extend that spring, well, there's going to be a force acting to return it to its equilibrium position. We're saying that that force is going to get bigger the more you stretch that spring. So F is proportional to the displacement, right? The definition here really just mentions extension, but the same thing would be true for compression. If we squeeze the spring really tightly, it's going to want to expand back out to its equilibrium position. So that would look something like this. Right, there's a really tightly wound spring. It wants to return back to its normal position of equilibrium. So there's going to be a force acting to extend that spring instead of compress it in this example. So that's the first part of our definition, that the restoring force F is going to be proportional to the extension S of the spring. The second part is that this is true provided that the elastic limit is not breached. So that basically, I'll show you a picture on the next slide, but it's when you extend the spring too much and it goes wonky and it doesn't go back to its normal shape anymore. So now the Hooke's law formula is actually pretty simple. It's F is equal to minus Ks. So we've talked already about how F, the force, is going to restore the spring to its equilibrium position. It's going to be proportional to the displacement, but the force also depends a bit on the spring. Some springs are going to be very stiff, so even with a small amount of extension, it's going to snap right back. So we have this thing here to account for K, which is our spring constant. So if we have a high spring constant K, it's a really snappy spring. It wants to go straight back to its equilibrium position. Whereas if it has a really low spring constant, it's much easier to extend that spring and to get it to, go through a much larger range while it's oscillating. Basically, the force will be a lot smaller for any given extension. There's a little yellow box over here. It's just a reminder, very similar to our formula for simple harmonic motion. A is equal to minus W squared S, where W is our funny omega one, the curvy W. So very similar to that formula, here F is equal to minus Ks, which just implies that the force is going to be in the opposite direction to the extension. So if we extend the spring downwards, like in this example here, well, the force is going to want to return it in the opposite direction, upwards. So here's, as promised, my little slide to demonstrate the elastic limit idea. Here's a spring that has not breached its elastic limit. Here somebody is basically pulled too hard on the spring and it's become deformed, it's gone past its elastic limit and it won't go back to its original shape. So that's also important to having your definition of Hooke's law, because the restoring force here is no longer going to be big, even when it's displaced past its equilibrium position, right? This has gone past its elastic limit, so now there's no restoring force even though the spring is extended. So make sure to add that into your definition. So here we have a fun slide with lots of patterns on it to try and make this seem more fun. Basically, it's a derivation. And it's any object that obeys Hooke's law. So if there's a typo there, the word or the letter L is missing. Any object, right, if it obeys Hooke's law, so most of the time that's going to be a spring, it's also going to then exhibit simple harmonic motion. So let's have a look at that relationship now. So we can see here our derivation. If an object is obeying Hooke's law, well then for that object F must equal to minus Ks. So the force, the returning force towards equilibrium, must be equal to some constant times by the displacement. And our force will be in the opposite direction to the direction of the displacement. So take a second to see what we've done to go from this line here to the next one. All that we've done is replaced F with ma, because we know force is equal to mass times by acceleration. So we get ma is equal to minus Ks. Now, you'll see where we're going with this in a bit, but we're going to make a the subject of the formula. So we divide both sides by m, and that leaves us with a is equal to minus Ks over m, because again we've divided both sides by m. So this follows on to the idea that a, our acceleration towards the equilibrium position, is going to be proportional to the displacement from the equilibrium position, which means that it follows simple harmonic motion. This next thing here is a little bit of a stretch, but you don't need to be able to do the in-between part. A then is equal to minus w squared, or angular velocity, times by s. So this all goes to show that if it follows Hooke's law, then it also obeys simple harmonic motion. So any spring that's oscillating about a fixed point, it's fair game to use any of our simple harmonic motion formula here. Now if you pay attention to the part down the end where a little bit of magic happens, what we're really seeing is from here to here, we're getting rid of our Ks, or our K over M. K over M disappears from here down to here, where we just say that A is proportional to S. And then something else reappears in between, and it's our minus angular velocity squared. So otherwise these are the exact same formula. A equals minus something times by S. In this case the something is K over M, in this case the something is angular velocity squared. So from here there actually follows on another formula that isn't in the log tables, so it's worth knowing that our angular velocity squared does have the same value as K, our spring constant, divided by our mass. W squared is equal to K over M. So we can see that formula here. W squared equals K over N, where W squared obviously is our angular velocity. You can just treat it as a constant here for simple harmonic motion. K is our spring constant, and M here is cut off, but it's the mass that's attached to that spring, right? So normally your spring is oscillating with a mass at the end. And then of course we have these few formulae that are applicable to any simple harmonic motion question. The first one here is the classic that really defines simple harmonic motion. A, your acceleration towards equilibrium position, is equal to minus omega squared s, or funny w, right? Where A is acceleration, W is our angular velocity, and S is displacement from the equilibrium position. The other all-time classic is T, the period, is equal to 2 pi divided by the angular velocity.